as we're looking at equivalent forces, you might come across this thing called distributed loading. So this is when we have, say, a beam or something like that that has a load distributed kind of across it in some kind of pattern following some kind of equation usually. Right, so this line on top represents an equation. We'll usually call that W. Some equation where there is a force acting over the beam distributed. So you can think of this in real life like when you have a snowbank, right? So the weight of the snow would be a force acting down on, say, your roof, right? And how we would represent that would be with this distributed load, where it can be evenly distributed, or you may have snowbanks that create these kind of equations where you have these loads that are not just a point force. It's not a force in one location. It's distributed over the area of the roof. So that's the idea of this distributed loading. And the way that we turn this into a resultant force, right, we want to change this into an equivalent force. So something where we have this loading and we make it just a single point force that is equivalent to the loading, but acting in just a single spot, right? It represents the overall load and how it impacts the object that it's on, right? The body, as a resultant force, right? So now instead of that shape that we have the remnants of that shape and just that resultant force that's acting on it. So we're going to talk about how we can find this. And really all it is going back to calculus. We're going to do some integrals, okay? Because all it is the area under the curve. If we find the area under this curve, this gives us the magnitude of the resultant force. Because this W equation is usually given in force per length. And then you multiply it over the length, right? You integrate over this length to find the area under the curve, and you end up with a force, right? You end up with your resultant force. So there is a calculus equation for this, right? So to find the magnitude of this resultant force, we take the integral over the length of W dx. And if you're not given an equation, you're given just maybe, say, a rectangular loading there. You can just say it's the integral of the area, right? All it is the area under the curve. That's how we find the resultant force. It's just the area of this shape that the loading has created. But if we want to find the location of the resultant force, so say, if I want to know what this x distance is here, I'll do that by using something called a centroid. Now, a centroid is just the location of the geometric center of a shape. So there's a handy table I believe it's in the back cover of your textbook. It looks something like this. It's this table that gives you where a centroid is for different standard shapes. So like, for example, if you're given a semicircular area, you can find the centroid is obvious, right? It would be halfway through the semicircle. But if you're given a quarter circle, the centroid is a little less obvious, right? And so you might need an equation for that. The centroid of a triangular area, we use that a lot. It's going to be 1/3 of the way of the triangle, 1/3 of the base, right? So if this were a triangular loading and this length was 3 meters and I had a distributed load across that 3 meters, my resultant force for that would be 1 meter in. So this chart can be really handy when you're dealing with standard shapes. But if you're not dealing with a standard shape and you have some curve, like this example here, that has an equation to it, there is an equation for the centroid, right? If you have some curve like this guy, there is an equation for the centroid, and that centroid equation is, write a centroid as x with a bar over it to show the center. So x with a bar over it represents the centroid, is going to be the integral of x times w, x times the w equation, dx, over the integral of w dx. Right, so this is over the area, that integral of x times dA, right, divided by the total area. So let's take a look at an example and how this centroid works, how we calculate this centroid with integrals. So this example is asking us to find the magnitude and location of the equivalent resultant force given by this distributed load. Right, so what we have here is a curved line. It's parabolic, right? Our W equals 60 times x squared. So it's this parabolic line going up representing the loading on this beam. This 240 Newton meters over here at the side tells us what the maximum is, right? So that is what the maximum loading, the loading at this point is. But the loading is represented by the equation 60x squared. So to find our magnitude, we can do FR is our integral, right, equal sign, our integral of the W equation, right, W dx. So I can take my integral along the length here, my integral from 0 to 2, right, we integrate along the length here, 0 to 2 of my W equation, 60x squared dx. And so when I take that integral, I'm going to get 60x cubed over 3 from 0 to 2. And then I just evaluate, right? So my 0, of course, takes the turn to 0. And what I get is my resultant force is going to be 60 times 2 cubed over 3, which is 160 newtons. 160 newtons, and that's pointing downwards, right? This loading is pointing downwards along the beam, so this resultant force is going to be downwards on the beam. This is FR. So now we need to find the location for this, right? We need to find this distance, x bar is the centroid. This distance of where FR is located. So we find our centroid equals the integral of x times w dx over this A that we found, right? Over this resultant force that we found. So we can either write integral of w dx, or since we already found it, we can write over 160. Right, so over here I'm going to do my integral, just kind of off to the side, my integral of x times 60x squared dx. Right, and of course that's also evaluated over the entire length of 0 to 2. So now I'm integrating 60x cubed, so what I get, 60x to the 4th over 4, evaluated from 0 to 2. So now my centroid, if I evaluate this, I get, what do I get? I get 15 times 2 to the 4th. So I get that. 15 times 2 to the 4th. I'm not sure what that works out to. I didn't write that step down. 15 times 2 to the 4th over 160. And if I simplify that, I get 1.5 meters. right? So this distance here is 1.5 meters in. That's where it's acting. It's acting 1.5 meters to the right of our leftmost side here, right? Our O, this is the point I was taking it about. That's how far our FR is located in. So these would be our two answers, right? Our 1.5 and our 160 newtons. So it's not too bad, right? These integrals should mostly be simple. Really, you're not going to find anything too complicated. In fact, doing the integration is the most complicated part of this, because many times we're going to have actually much simpler shapes than this. We might have a distributed load that's just completely straight, right? So the representation of the equation might just be a single number where it's evenly distributed throughout the whole thing. So we just have a square or a rectangle, which then we can take the area of very easily. Or maybe triangular loading. These are very common. It's very common to see things just show up in basic shapes rather than being represented by these equations. But it's important to know that this is how we get there. We get there through this integration. But let's take a look at kind of a more simplified example where integration may not be necessary. This example again asks us to find the resultant force and specify where it acts on the beam from point O, but it's a much simpler system. What we have are these straight lines. These are straight lines leading up from point O up to this peak here of 3 kilonewtons per meter. And what this is telling us is that these are actually two triangles, right? These are two triangular areas that represent the distributed loading. So let me kind of just redraw this in a simplified form. Right, so here's my beam. I'm just gonna say, I'm gonna draw kind of the dotted outline of this shape. But really what it is I have two areas here. This is area 1. And this is area 2. Right? It's two separate triangles. Right? I can make two separate right triangles for this. And that makes it really easy to find the area under the curve because I know the peak of both of those triangles is 3. And I know how to find the area of a triangle, right? Area of a triangle is 1/2 base times height. So for A1, my height is the 3 kilonewtons per meter. Right? 3 kilonewtons per meter. And then my base is this base length here of 3 meters. So times 3 meters. So for area 1, what I get is 4.5. 4.5 kilonewtons. And that is the resultant force, right? The area, this is the resultant force. It's 4.5 kilonewtons. And we know where this acts, right? We can look at our centroid table, and we said it acted as 1/3 of the length inwards. From the tall peak, it acts in 1/3. 1/3 of the base. So if this is 3 meters, it's acting 2 meters over, right? Because this would be 1 meter away from the highest point of the triangle. So it's acting here 2 meters to the right of our point O. For our second area, we still have the same height, right? 3 kilonewtons per meter, but now the base length here is only 1.5. 1.5 meters. So my second area is 2.25 kilonewtons. And that is going to be acting right here, 2.25 kilonewtons. And I can again find this distance, because it will be, again, 1/3 of the way in for a triangle, just for a triangle. Right? That's always where a centroid of a triangle is located. So that is going to be 1/3 1.5, 0.5 meters, right, from the triangle split. So that's the location of it. And now what we can do, since we have simplified the distributed loading, all we need to do to get the resultant force is add those two forces together, right? It's just the sum. The sum of our forces is going to give us the resultant force, right? So 4.5 plus 2.25. My resultant force is going to be 6.75 kilonewtons acting downwards, right? So that's our resultant force. For our location, we can do a few different things. We can do the centroid integral if we so desire. It would be a lot more complicated to do it that way. So instead, we can use the method that we just learned in equivalent forces, where we take the moment. We take the moment about point O, and then find where this resultant force, where does this FR act, right? So what I'm going to do is I'm going to take a moment about point O. Get all of these guys out of the way. I take a moment about point O, and I'm going to make, in this case, I'm going to actually make clockwise positive, because I can see if I take this moment about O, my two resultant forces, my 4.5 and my 2.25, are both acting downwards, and so if I make this clockwise positive, I'll end up with positive moments, and it'll just be a little easier to work with. So the moment about O is going to be those resultant forces times their distances, right? So I was writing down these distances for a reason, because I was going to take a moment about this point O here. So I can do, my moment about point O is going to be 4.5, right? That's our A1 force times the 2 meter distance away from point O, plus 2.25 times the 3.5 meter distance from point O. Right, so I can still use those simplified loadings from those distributed loads. Those two forces that we found by breaking up the distributed load, I used those to find my moment, which I get is 16.875 kilonewton meters when I plug that into my calculator. And so I can use this number, and I can say, okay, well, where is this acting? If I say M equals FD, my F was this 6.75 kilonewtons. So to get my distance, I just do moment over F, which is 16.875 over 6.75. And I get that it is acting at a distance of 2.5 meters to the right of O. These in the boxes would be my two answers. Let's go ahead and take a look at one more example. In this example, I'm again finding the resultant force and specifying where it acts, but now my distributed loading looks a little bit different, and I have just a regular applied point force, right? A force applied at a point. So we'll notice that we actually have two numbers on this loading, right? On the far left, we have 20 pounds per foot, and then on the far right, it says 5 pounds per foot. So what this actually means is that it's not going all the way down to 0, as it did in our last one, right? Our endpoints were both 0 with a peak of 3. But this is going from 20 to 5. So when we break this down into these areas, we should keep in mind that our area 1 is this top triangle that has a rectangle underneath it, right? A rectangle with a height of 5. This is a height of 5 rectangle. And then our triangle component is actually minus that 5 to get this triangle, right? So this is actually 15 tall. 20 minus the 5 gives us that this triangle is 15, while this bottom shape, this bottom area, is going to be 5 tall, and it's both over the 9 feet. So when I do these two areas, right, let me do the rectangle first, right? That's a really easy one. This is A1. And I'll call this guy A2. So A1 is going to be just base times height, right? So 9 times 5. Easy enough. I find the resultant force from this is 45, right? 45 pounds. And it is acting right in the center, right? It's acting halfway in the middle of that shape. And that's what we expect for a rectangle, right? The center of the rectangle to be exactly halfway between each side. So this distance is 4.5 feet, right, for this 45 pounds. 45 pounds. Now we'll look at our second area. It's this triangle here, and we'll do the 1/2 base times height. That's area of a triangle. 1/2. The base is the 9, this 9 distance here. And the height is 15, right? It's that 20 minus that 5. And so I can punch all of that into a calculator and get 67.5 pounds. Right? And we said that was acting in 1/3 of the way. So this force, 1/3 of 9, is 3. It's acting 3 feet inwards. Let's pretend like that's a better looking 3 than it is. 3 feet. So now, instead of the triangles being side by side as they were in the last example, it is a stacked triangle over a rectangle. All we did was break it into shapes, so we didn't have to do any complicated integration or anything. So that gives us our resultant force, right? We can get our resultant force from this. Our resultant force is going to be that 45. If I make downwards positive, 45 plus 67.5. And then don't forget this 50 guy over here, right? Just an applied force. Plus 50. Right? Everything is pointing downwards. So our resultant force is going to just be 162.5 pounds. Acting downward on the beam. And then we can repeat the same process that we did in the last problem, taking a moment about point O so that we can find wherever this resultant acts, right? So I'm going to take a moment. A moment about O is going to be 67.5 times this 3 feet distance that we found. 4.5 times the 45 pounds. Those were our two resultant forces. And then don't forget the 50 pounds again. Plus 50 times that distance is 9 plus 5 is 14. So I get that the moment is 1105 pound-feet. And then again, I know moment is force times distance. So my distance will be 1105 over 162.5. And so I will get a distance from O of 6.8 feet. 6.8 feet to the right of O. That's it. Those are my two answers there. So we'll look at one final example where we have not loading in just one direction. So far, all of our loading has just been downward in the y direction, but let's take a look at one where we have loading in the x and y direction. In this last example, it asks us to find the resultant force and specify where it intersects member BC. So that's this member right here. So where does it intersect the vertical portion of this little L-shaped contraption, right? Our little L-shaped beam here. Where does the resultant force interact with this? So first things first, of course, is going to be finding the resultant force, right? So we can simplify this system into the resultant force for the rectangular shape on top and for the rectangular shape on member BC. So our top one here, from A to B, we have 3 kilonewtons per meter times 3 meters. It's a rectangular shape, so it's just going to be the base times the height. So we're going to end up with 9 kilonewtons. 9 kilonewtons is the resultant force. And then this distance, of course, will be 1.5 meters. Halfway through member B. Our next resultant force is this 2 kilonewtons per meter, right? This 2 kilonewtons per meter acting over this 4 meters. So 2 times 4 is 8. It will be 8 kilonewtons. And it is acting 2 meters upwards from C or downwards from B, right? It's acting halfway between. But is that where the resultant force overall is acting, right? It's not. That's only where this 8 kilonewton force is. It's acting 2 meters from B or from C, but only that component of it. What we need to do is we need to take the moment and then determine where the overall resultant is interacting with this, right? So if I take a moment, I don't want to use that color. Let me take a moment about point B, right? That's where I'm measuring from. That's where I'm interested in. If I take a moment about point B, I'm going to get 9 kilonewtons times 1.5 meters, right? That's the distance here between B and the 9 kilonewtons. And then I will do the 8 kilonewtons, right? This one is going counterclockwise. This one is going clockwise, however, so minus 8 kilonewtons times this distance of 2 meters. 2 meters away. So I get a moment about B is negative 2.5 kilonewton meters. Right, negative 2.5 kilonewton meters. So from there, I'll say moment is force times distance, or my D, my distance from B is going to be the moment over the force. So my negative 2.5 over 8 gives me a distance away from B of 0.31 meters. 0.31 meters below point B. So again, when I write this resultant force, we found the distance. When I write the resultant force, I can write it in a few different ways. I would write my resultant force is negative 8 I hat minus 9 j hat kilonewtons. Right, that would be my resultant force. Or I could give a magnitude. I could give a magnitude and direction. And then I give my D here. It is acting somewhere right about here. Something like this. This is where my resultant force is acting. 0.3 below B. So not as intuitive as we thought it was, because that 9 kilonewtons is influencing where the resultant force is actually acting. What we get is this result. So the general process is take an integral if you have to find the centroid. But if not, use the areas. Use the areas to find your distributed loadings. Simplify your distributed loadings. Then find your resultant forces. And if you need to specify the distance, use moment equals F times d to specify where that force is acting on your member.